Okay, I completely forgot to do this video last week. Oops, sorry. This is about electrode potential. This is the second half of section 2, I think, of the book. When I talked about galvanic cells. And we had mercury batteries. Yeah, so this is, the second half of section 2. Yeah, okay. So in an electrochemical cell, the very first one that I talked about in the section 1 video, if there are two electrodes, we have zinc and copper. The two metals have different tendencies for accepting electrons, as we talked about. I don't remember which video it was, but some video that's talking about the reducing and oxidizing potential, the reducing agents in the last chapter, the oxidizing and reducing agents. And there was a chart that showed you, let's see if I can find it, the different tendencies of, here on page 607, the relative strength of oxidizing and reducing agents, this table. But also remember from the last section that I told you that half cells are written as reduction potentials. And so this is going to explain why that is, because we compare electrode potential when it comes to reduction, which is accepting electrons. So reduction potential is the tendency for a half reaction of a metal to happen as a reduction half reaction in an electrochemical cell. So here we have the electrochemical cell again. Remember, there are two half cells. We have the anode, which is the oxidation half cell, and we have the cathode, which is the reduction half cell. So we have the strip of zinc. Let me get my little laser pointer. We have the zinc metal in a solution of zinc sulfate, and we have the copper strip in a solution of copper sulfate. So electrons are going to move from zinc to copper because copper has a higher reduction potential, and zinc has a tendency to be oxidized, so it's going to lose electrons to copper, which means the electrons are going to combine with the copper ion here. So the half reaction is going to be Cu plus 2 electrons. Gives you copper metal. And then over here, zinc is going to be reduced. So oxidized. So you have zinc is going to form the zinc ion. That looks like a 2, but it's really a Z, plus 2 electrons. So we have oxidation happening on this side and reduction happening on that side. So the electrode potential is the difference in potential between an electrode and its solution. So each half cell is going to have its own potential. When these two half cells are connected and reaction begins, the difference in potential is observed between the electrodes. That is measured in volts, which I'm assuming you have learned about voltage in physics, maybe? Voltage is a measure of energy required to move certain electric charge between electrodes. So potential difference is measured in volts.
When the flow of electrons from these kinds of reactions are sent through a conductor, like a piece of metal, it can be used to do all sorts of work, like, for example, this kind of work. The amount of work that can be done depends on how strong the push or pull on electrons is between the two reactants. This is the reaction's electrical potential, but to its friends, it's known simply as voltage. Basically, if the voltage is high, each electron can do a lot more work than if the voltage is low.
Okay, so that's basically the practical application of measuring electrode potential, is because the higher the difference between the two electrodes, the more potential there is to do work, which is why it relates to the voltaic batteries that I talked about in the last video last week, because we have different voltages of battery. We have the 1.5 volt battery, which you see in AA and AAA, and we have those rectangular batteries that have 9 volts. So they have the potential to do more work. So in order to measure the voltage, we connect a voltmeter in the middle of the electrochemical cell. So the voltmeter connected across the copper zinc voltaic cell measures the potential difference of about 1.10 volts when each solution concentrations are 1 molar each. So again, we have the anode on the left-hand side, we have the cathode on the right-hand side. The anode is where oxidation occurs, the cathode is where reduction occurs. So in this particular electrochemical cell, zinc is being oxidized and losing electrons. Those electrons flow through the wire, through the voltmeter, and then they reduce the copper ions on the cathode side. The potential difference measured across voltaic cell roughly equals the sum of electrode potentials for the two half reactions. So this is really quite a simple concept. It is easy to measure the voltage across the voltaic cell, but there's no way to measure individual electrode potential directly. Remember, individual electrode potential is the electrode potential of just one half cell. There's no way to measure that directly. The only way that we can measure anything directly is between the two half cells. But how do we measure just the electrode potential of just one electrode? We can't, because there's no transfer of electrons unless both the anode and the cathode are connected in a complete circuit. If you just stick a strip of zinc in a solution of zinc sulfate and connect a voltmeter, there's no flow of electrons, so you can't measure anything. So a relative value for potential of a half reaction can be determined by connecting it to a standard half cell as a reference. This is called a standard hydrogen electrode, or SHE. A platinum electrode is dipped in a 1.00 molar acid solution, and it's surrounded by hydrogen gas at 1 atm and 25 degrees C. Other electrodes are ranked according to their ability to reduce hydrogen under these conditions. So the standard hydrogen electrode is the standard, and then we connect other metals and we measure the potential difference. The anodic reaction for the standard hydrogen electrode is described by a forward half reaction in the following equation. So we have hydrogen becoming the hydrogen ion and being oxidized and releasing 2 electrons. Remember, we are measuring the potential for metals to be reduced. The cathodic half reaction is the reverse, because remember, let me just go back to here. Because we're talking about anodic reaction. Anode is oxidation, so that's this one. The cathodic, which is reduction, will be 2H plus 2E yields H2. That's the cathodic half reaction. A random potential of 0 volts is assigned to both of these reactions. Any voltage measurement is credited to the half cell connected to the standard hydrogen electrode. The standard electrode potential, or E0, is a half cell potential measured relative to a potential of 0 for the SHE. Electrode potentials are always expressed as potentials for reduction. These provide a reliable indication of the tendency of a substance to be reduced. Positive electrode potential values indicate that hydrogen is more willing to give up electrons than the other electrode. Half reactions with a positive reduction potential is favored. So that's important. Positive reduction potentials are favored. So here's an example of a copper strip being connected to the standard hydrogen electrode, and the voltage that's measured across that has a value of positive 0.34. Half reactions with a negative reduction potential is not favored. So these half reactions prefer oxidation over reduction. So remembering that our electrode potentials are measured as a tendency to be reduced. So if the electrode potential is positive, that means that that metal likes to be reduced. If the electrode potential is negative, that means that metal does not like to be reduced and it prefers to be oxidized. Negative E0 values indicate that the metal or other electrode is more willing to give up electrons than hydrogen. So in this example, zinc is being hooked up to the She, and the voltage that's measured here is negative 0.76. That means that zinc compared to hydrogen would rather be oxidized and hydrogen will be reduced. So this is a table that's in your book of standard reduction potentials. Let's see, what page is it on? It is on page, drum roll please, 626. So you will always be given a table if I ask you to calculate the electrode potential of a cell. What you'll be doing is basically looking at this, this table and looking up the potential for each half reaction. And in a second, I'll explain how you calculate the value for the entire electrochemical cell. When a half reaction is written as an oxidation reaction, the sign of the electrode potential changes as shown for the half reaction for zinc. So if you write it as a reduction potential, which is in this equation, the E0 value is negative 0.76. But if you write it as oxidation, of course, you reverse the equation, which means you reverse the sign. It's kind of the same theme that we had with Hess law and I forget the other one that we did. But basically, it's the same theme throughout chemistry. If you reverse the reaction, you reverse the sign of delta H or whatever it is. To measure the reduction potential of the zinc half cell is connected to the She. And like I said, the potential difference you can see from the voltmeter is negative 0.76. The negative number indicates the electrons flow through the external circuit from the zinc electrode, which is oxidized because of the negative electrode potential. That means that zinc is going to be oxidized. The electrons flow from zinc to the hydrogen electrode, which means the hydrogen ions are reduced. Now, one thing that you might be asking yourself for the She, how do we actually reduce hydrogen ions? Where does that come from? Because I told you it was a platinum strip surrounded by hydrogen gas, but don't forget it's a platinum strip submerged in acid. So your hydrogen ions are going to be in that acid. When the copper half cell is paired with the She, it gives a electrode potential of positive 0.34. So the positive number indicates that the copper ions are more readily reduced than the hydrogen ions. Standard electrode potentials can be used to predict if redox reactions will happen naturally. So a lot of times I indicate to you guys like, okay, so why are we learning this? What's the point? This is the practical application. A naturally occurring reaction will have a positive value for the electrode potential for the cell according to this equation. So the electrode potential of the whole cell is equal to the electrode potential of the cathode minus the electrode potential of the anode. And the next question you might have is, well, how do I know which cell is the cathode and which cell is the anode? I will tell you. So cathode minus anode. When evaluating the two half reactions of a cell, the half reaction that has the more negative electrode potential is the anode, okay? Because remember, negative wants to be oxidized and oxidation happens at the anode. So it makes sense. If you're comparing the two half reactions, you go back to this table in your book and you look at the standard potential for each of the half reactions. The one that has the more negative half reaction is the one that's more likely to be oxidized, and therefore it's the anode. Okay, I don't think it's table 19.4. That's the old book. This is figure 2.10. I should really change that. When the reaction is reversed, the actual half cell potential is the negative value of E0. The total potential of a cell is calculated by subtracting standard reduction potential for the anode from the cathode. That's what I said before. E0 cell equals E0 cat minus E0 an. Example, let's say a cell is made from iron in a solution of iron nitrate and silver in a solution of silver nitrate. So if we look at figure 2, 2.10, we have these two values. Remember, they're written in potential for reduction. So of course, both of these equations are reduction half reactions, and you get your E zeros. So you look at which one is more negative. Well, of course, that would be iron, because iron is the only one that's negative. So that becomes the anode. So if we have E0 cell equals E0 cat minus E0 an, the more negative value is the anode. So we're going to get, okay, who cares about the overall reaction? Oh, hold on. I should actually do that. Okay, wait. Let me go back. Baby steps. Otherwise, you're going to be like, what? Okay, so here's the equation. Oh, you have to notice that in order for the electrons to balance, the silver half reaction is multiplied by 3, but we do not multiply the electrode potential. That's a big difference. So the iron in iron nitrate is the anode because it has a lower reduction potential, which makes silver the cathode. So the overall cell reaction is just adding those two together, of course, because the electrons cancel out. Now, the reason why we reversed this equation, right? So you see that the iron solid is on the right-hand side in the electrode potential equation, but we've put it on the left-hand side in the overall equation. That is because it is the anode. An anode is oxidation, which means that the first equation has to be reduced. Okay, so again, our overall equation, the reduction of the silver ions is multiplied by 3, like I said, so that the number of electrons lost in that half reaction equals the electrons gained in oxidation. No, sorry, that should be reversed. Okay, anyway. Okay, so the standard reduction potentials for the anode and cathode are the same as we did before. I'm just pointing out that in order to account for having lost 3 electrons from iron, silver has to gain 3 electrons. So you have to multiply the silver half reaction by 3. But when a half reaction is multiplied by a constant, the E0 values are not multiplied. So that would be a big difference from what you're used to before. So the potential for this cell can be calculated as follows. Remember, it's cathode minus anode. The cathode was silver, the iron is the anode, so it's 0.8 minus a negative 0.04, and that is 0.84 volts. Remembering that a positive voltage means that the reaction will happen naturally. If the calculated value for the electrode potential of the cell were negative, the reaction would not happen naturally. So it would not happen in a voltaic cell. And this is why it matters, because if you want to develop a new type of battery, maybe one that's more efficient, maybe one that has a higher voltage that can do more work, you have to study this topic. You have to be able to determine the electrode potential difference between your cathode and your anode, as I discussed in the last video about what we make in batteries, what we make the cathode and what we make the anode. You want to make batteries efficient. So if you chose 2 metals that have a negative voltage and you make a battery out of that, it's not going to work because those reactions are not spontaneous. So that would be stupid. That's why we have to study electrode potential in order to develop new and better batteries, because if E0 is negative, it's not going to work for a voltaic cell, but it can be made to happen in an electrolytic cell, which is the topic for the next video. The next video.
Here we go.
if I have solid copper sitting in copper sulfate and solid iron sitting in iron sulfate, which way is the reaction going to go? Is the copper going to lose electrons, or is the copper going to gain electrons? Is the iron going to lose electrons, or is the iron going to gain electrons? Really, the only way to figure this out is to figure out something called E cell. And we do that by writing down the half reactions that we think are going to happen, looking them up in a table of reduction potentials, and then adding them together to see what value we get for E naught cell. Let's try this one. I'm going to assume in this case that the copper gains electrons to make solid copper, and that the iron loses electrons to become iron 2+. This is a reduction. This is an oxidation. To figure out whether or not this reaction happens as I've written here, I have to look up each reaction in a table of reduction potentials. Copper 2 plus 2 electrons makes solid copper. In my table of reduction potentials, I find copper 2 plus 2 electrons makes solid copper. And that gives off 0.34 volts of potential. 0.34 volts. Now here I've got iron becoming iron 2+ and 2 electrons. What I have written in my table of reduction potentials is not that. I've got iron 2+ and 2 electrons becoming solid iron. That's the exact reverse. The reason is, this is a table of reduction potentials. These are all reductions or gains of electrons. This here is written as an oxidation. So, if I flip this, I get Fe arrow, Fe2+, which is what I have here. So what I have to do is flip the sign of the voltage. This becomes plus 0.44 volts. Now, what's important to note here is that when I add these two reactions together, I have 2 electrons on the left and 2 electrons on the right. Copper 2+ and 2 electrons and Fe solid all on the left becomes copper and Fe2+ and 2 electrons all on the right. But 2 electrons on both sides will cancel each other out, and I'm left with the overall reaction for the cell. What is E cell? E cell is what I get when I add these together. 0.34 plus 0.44 is 0.78 volts. So this overall redox reaction has an E cell, or standard cell potential, of 0.78 volts. This is a spontaneous reaction, or it happens exactly as I've written here, because E cell is positive. Positive E cell means it happens as written. What I want to show you is, what if I guessed that it had happened the opposite way? Instead of copper 2 and iron, we started with iron 2 and copper. Well, we look up each half reaction in the table of reduction potentials. Iron 2 and 2 electrons combine to make iron. That's negative 0.44 volts. And I have copper becoming copper 2+ and giving off 2 electrons. I have the opposite reaction here, so I have to flip the sign of my potential. This is actually negative 0.34 volts. When I add this reaction together, Fe2+ and copper and 2 electrons on the left, Fe and 2 electrons and copper 2+ on the right. Oops, didn't mean to cross that one out. My total E cell when I add these up is negative 0.78. This is not spontaneous. It does not happen as written, because E cell is negative. you're going to have to remember negative E cell, not spontaneous, positive E cell, spontaneous. But what you'll notice is, if I can find my old sheet, that copper 2 mixed with solid iron is a spontaneous reaction, but copper mixed with iron 2 is not a spontaneous reaction. You'll have to take an educated guess about which is going to happen, figure out your E cell, and make sure that it's positive if you want to predict which direction your reaction goes in. So, to wrap this up, it's not spontaneous when you mix solid copper with iron 2, but it is spontaneous to have iron become iron 2 plus and copper 2 to become copper. So, what's happening in this cell is that copper 2 plus is becoming copper and iron is becoming iron 2. Just found that out. So, this one is giving off electrons, this one is absorbing electrons, and the direction of electron flow is from where it's being given off into where it's being absorbed. Hey, best of luck to you when you're using reduction potentials to figure out if a reaction is spontaneous or not. Cheers.